Every time you use your smartphone, you are interacting with a hidden, microscopic metropolis. Beneath the glass of your screen lies an organized grid of electronics that allows every tap and swipe to happen. Building electronics used to be a messy, manual process. Early machines relied on point-to-point wiring, where individual cables were tied by hand to every single part. This created chaotic webs of wire that were difficult to build and even harder to fix. The printed circuit board, or PCB, solved this by taking that tangle of cables and flattening it into a reliable, rigid structure. It turned chaotic wiring into a permanent, compact infrastructure. A PCB does two basic things. First, it acts as a stiff foundation. It provides a solid surface to hold dozens of tiny, fragile components in their designated spots, much like the bedrock of a city. Second, it creates the electrical connections between those parts. The board itself contains a built-in highway system that routes signals through solid metal, removing the need for any loose wires. This urban grid allows thousands of electronic buildings to sit on a surface smaller than a credit card while communicating with each other at the speed of light. A PCB has 4 layers. First, the substrate acts as a stiff bedrock. Next, a copper layer is etched into traces, highways for signals. Then, the green solder mask breaks insulates these traces, preventing short circuits. Finally, the white silkscreen adds decks to guide component assembly. These 4 layers, the stiff base, the copper highways, the green insulation, and the white signage, create a durable environment ready for a complex electronic system. Once the board is ready, we add components. Resistors and capacitors manage power, while integrated circuits, or microchips, serve as the device's brain. These parts are soldered onto the board at specific connection points. The solder mask covers everything else, so components only attach to intentionally open spots. When the device is powered on, an electrical signal leaves one chip and travels along a specific path to arrive at another. Because this route is fixed in solid copper, the signal reaches its destination with very little energy loss and no outside interference. Simple devices may only need a single layer of copper, but as devices get smaller, we use double-layer boards, placing conductive highways on both the top and bottom. Complex devices use multi-layer boards. Designers stack these copper highways on top of each other to create a sprawling 3D metropolis. To connect layers, they use vias, microscopic elevators that allow signals to drop from a top-layer trace to a path in the middle. Stacking layers and connecting them with vertical vias allows us to pack massive amounts of computing power into the small devices we use every day. Designers use specialized software to map out these 3D cities, planning every connection digitally before the physical board is ever manufactured. During this planning, engineers must manage traffic challenges. They distribute power evenly, prevent electrical noise, and ensure parts can cool. A successful layout keeps the electronic city running smoothly, without overheating or signals getting lost in the noise. In wireless and 5G devices, these design rules become even stricter. These systems use radio frequencies, where signals travel at incredibly high speeds. At these speeds, designers must focus on impedance matching. This means the electrical resistance of the copper trace must align with the signal's rhythm. If the trace is sized incorrectly, the signal hits a bottleneck and bounces backward, distorting information. When signals bounce, they create interference waves, causing signal integrity issues, where noise from one trace spills over, disrupting nearby paths. In modern wireless systems, the physical shape and size of the copper roads are just as important as the microchips themselves. The PCB is the vital infrastructure of the modern world. It provides the foundation and the connections that transform a collection of separate parts into a single functioning system. We have moved from massive cabinets full of tangled wires to microcircuitry that fits in the palm of your hand. This progress is what makes our compact wireless world possible. In our next video, we will dive deeper into the world of high-speed signals and explore how engineers master the physics of signal integrity. Thanks for watching.